In this example, we're going to consider a differential equation which has a non-constant coefficient. In particular, it has this t multiplier that we fortunately just learned how to handle in terms of Laplace transforms. With that in mind, we're going to go through our usual steps, starting off with the Laplace transform of the entire differential equation. The transform of y double prime is our s squared y of s minus s times 0 minus another 0. These are our y of 0 and y prime of 0 values, which are given. Then we're going to have plus 2 times the Laplace transform of ty prime. We'll take a closer look at that in a moment. For now, we'll keep going with the other terms. And the last term on the right-hand side, the transform of 1, is simply 1 over s. Now, inspecting more closely this transform of t times y prime, that is going to give us, based on this rule up here for the t times any function, 2 times negative 1 times the derivative with respect to s of the Laplace transform of y prime. So the same function here, but without the t. And we know how to compute that. That's going to be s y of s minus 0 for the initial condition. And then we're faced with something new again, but this isn't too bad. This is simply a product rule. We have two functions of s now, and we have s times y of s, so we're going to use the product rule. And that's going to give us y of s, the derivative of the first times the second, plus the first times the derivative of the second. And what that boils down to overall is s squared y of s minus 2 times y of s plus s y prime of s minus 4 y of s equals 1 over s. So we've been able to handle that non-constant coefficient, and it gives us terms related to the unknown y of s. Here's that same expression again, and what we're going to do is gather terms like usual. So we'll have an s squared minus 2 minus 4. Those are all the terms with y of s's in it. There's 3 of them. Then we're also going to have a y prime of s term that's by itself. Now that's an interesting option. Let's rewrite that because this is new. This is something that has a derivative of y in it, but y in this s variable. We don't really know how to solve for that yet, but if we put it in a different form, we might be reminded of an earlier technique. What I'm going to do is write that y prime of s first, and then we're going to divide through every term by negative 2 over s, or 1 over negative 2s. And what that's going to give us is 1 y prime. Then we're going to have s squared over negative 2s, that's negative s over 2. And this is negative 6 over negative 2 will be 3 over s times y of s. And then 1 over negative 2s squared. Now this, aside from the fact that the variable is an s, should look familiar, because this is simply a first order linear differential equation in y of s. Hey, we've solved these before. We've solved these using integrating factors. That's that u, this time as a function of s, which is e to the integral of whatever is in front of your y of s. This is the standard form that we're in right now. Standard because the y prime just has a 1 out front. And so we can construct this integrating factor, and as we'll see, it's going to help us simplify this differential equation. Now, first order, we started with second order, we're now in first, so it's a step forward, but it's still not trivial to solve. Calculating through on this, we're going to have negative s squared over 2, s squared over 4 rather, another 2, plus 3 ln of s. And when we have the exponent, we can break it into the two terms multiplied. E to the 3 ln of s. And the e to the ln are inverses, so that'll give us s with these two things here combined. And then we had the cubed, so we end up with s cubed times this other exponential. And if you recall, the purpose of having this integrating factor is it's something that we multiply both sides of the standard form by, and it will lead us to an exact form that we can easily integrate. So we're going to multiply both sides of the exact form, which is number 1 here. And we're going to go term by term, so we'll have an s cubed e to the negative s squared over 4 y prime plus negative s over 2 plus 3 over s multiplied by this integrating factor, and then times y of s, and negative 1 over 2s squared times the same thing, e to the negative s squared over 4. Now that may not look like it helped immediately, but if you take a look at this first term and this related first term here, they're actually related by a derivative. If you take the derivative of this and use the product rule and expand and carry on, you will end up with this term here. Likewise, the y and the y prime are related through an s derivative. So what we have here is a product rule on the left-hand side. And so what we can do is rewrite that without changing anything as simply the s derivative of s cubed e to the minus s squared over 4 times y of s. And the right-hand side stays exactly the same. S squared over 4 there. Now we can do a little simplification here, getting rid of the powers of s, but we don't actually do any transformations. The left-hand side we're simply rewriting as the derivative of a product, which is what this more complex looking form actually is, or can be written as. We'll move on to the next page and see how that helps us. Tidying a few terms up here, we end up with this form of the equation, and then we simply integrate both sides with respect to s. Now the left-hand side is easy. The whole point of the derivative and integral combo is that they're inverses of each other. They cancel out. And then we end up with exactly the same expression we had before, but without the derivative. And the right-hand side we have to be careful, but we can integrate this. Notice the s squared with the s out front. This is the classic integration by substitution. The only thing we're going to need to add here is a negative 2 to make that work. If we differentiated this exponent, we'd end up with a negative 1/2 popping out. To cancel out, we have a negative 2. Or if you want, you could just use the negative 1/2 that's there. The key thing is that the integral is a fairly simple form by the time we're done. And lest we forget, we've just integrated, so we need the plus constant. So finally, we end up with y of s, which is equal to, what we're going to do is divide both sides by s cubed e to the negative s squared over 4. Do the whole thing here, divided by s cubed e to the minus s squared over 4. And what that gives us is 1 over s cubed plus c over s cubed e to the minus s squared over 4. So one of these is handy. One of these we know how to inverse transform. This term is trickier and also involves knowing our theory. The issue being if we're dividing by e to the negative s squared, that's the same as multiplying by e to the s squared over 4. And for this to be of exponential order, the only way that's going to work, because it's not exponential order here, because of that squared, the only way to make this work so that the entire expression is of the correct order that we can do transforms on it, we need c equals 0. That's the only way to get rid of this term and have it go away. So y of s is simply 1 over s cubed. That also simplifies our life immeasurably when it comes to the inverse transform, because it means y of t in this case is the inverse of this, which is t squared, and we need a 1/2 to make that work, because we need a 2 on top to make the transform work correctly. So 1/2 t squared is our solution. Well, does that make any sense? Let's verify that before we wrap this problem up. We started off with this differential equation, and we're proposing that y equals 1/2 t squared is our solution. To sub that in, we're going to need y prime, which is 2t over 2, which is just t, and we're also going to need y double prime, which would be simply 1. All right. Then our left-hand side of the differential equation up here is simply 1 plus 2t times t minus 4 times 1/2 t squared. We can simplify that a little bit. We have 2t squared minus 2t squared, which is equal to 1, which is equal to our right-hand side. Big check mark. So our technique for handling this t times a derivative of y, just using the Laplace transform rules, worked like a charm.